So now it comes our third paper, DynPRE. It talks about protocol reverse engineering through dynamic inference. Our speaker, Zhen Xiong, is a student from Tsinghua University who focuses on protocol security with fizzing and reverse engineering. Let's welcome our speaker.
Okay, thanks for the introduction. Hello, everyone. I'm Zhen Xiong from Tsinghua University. Today, I'm going to introduce our work on protocol reverse engineering. This is a joint work with Central South University. Protocol reverse engineering helps to understand unknown protocol specifications. It serves as the base for various applications and analysis, such as product testing, model checking, and code generation. Existing methods can be divided into two categories based on the input, that is the network traces and the program analysis. The program analysis-based approach analyzes the reverse the protocol by using the techniques such as taint analysis. They require access to the source code or the binary, which is not always infeasible in practice. In this work, we introduce a protocol reverse engineer tool based on network trace. So let's see how traditional network trace-based methods works. Those methods use statistical analysis of the input network traces. For example, alignment is a widely used approach to mining the format features presented by the message in the traces. For the two messages above, the result after alignment is shown below. The method adds padding character where necessary to align these two messages as closely as possible. It then merges the conceived bytes that are either identical or variable to obtain the inferred format. As shown in the figure, the inferred format consists 9 fields. However, these methods often lack accuracy for two reasons. First, to achieve optimal performance, these methods usually require high-quality network traces with diverse protocol messages. Failing to do so often results in incorrect partitioning. As an example, look at the message with the correct format shown in the right. Let's break down the structure of the first 4 bytes. This consists of a 1-byte type field and a 3-byte length field. If in all input messages, the highest byte of the length field is always 0, and the lower 2 bytes vary, then this different distribution can cause the traditional method to incorrectly regard those 2 paths as separate files, as shown in the figure on the left. However, the correct partition should be like this. For the second limitation, these methods are not accurate enough to capture the semantics of the fields, since the same value of the bytes doesn't mean the same semantic. That is, there is a gap between the file semantic and the file value's statistical features. As for the insight of our work, we find that in many protocol reverse engineering applications, such as protocol fuzzing, server's interactive capability can be exploitable. Through interaction with the server, we can obtain additional message samples. More importantly, we can extract semantic insights from the server because it already encodes the protocol logic. Therefore, we can utilize this interactive capability for reverse engineering. To achieve this approach, we need to address 2 challenges. First, how to interact with the server. Since the server is a stateful system, it usually requires well-formed messages in a specific sequence. For this problem, the input network traces can be used as a reference. since they are records of actual client-server conversations. However, we need to consider the validity of session-specific identifiers. This is a widely used mechanism in protocols. An example is the cookie field in HTTP protocol. The second challenge is how to explore the interactive server in an effective way to understand the protocol. The strategy should be generic and effective. In this work, we developed a protocol reverse engineer tool called DynPRE. It incorporates dynamic inference for more accurate analysis. At a high level, it contains two modules. The first module is the session-specific identifier detector. It is designed to address the first challenge of proper interaction. And the second part is the dynamic inference module. It's designed to address the second challenge of effective semantic exploration. Let's start with the first module. First, what's a session-specific identifier? This is a special field dynamically assigned by the server to keep track of the context information for each session. Once assigned, the subsequent request should contain valid values for these fields. Otherwise, the server will reject the request. For example, the session ID in the right figure is a session-specific identifier. The server assigns its value at point 4, and this value is used in the subsequent interactions, as shown in the red. The source here is the location that first introduced the dynamic value, and the reference is the subsequent location that consumes that value. Here, the tree ID field is also a session-specific identifier. Meanwhile, the constraint relationship between the source and the references can be diverse. Here, the session ID and the tree ID are equivalence relations. There are also other relations, such as +1 relations. Meanwhile, different identifiers may have different lifetimes, as demonstrated by the session ID and the tree ID. To detect the session-specific identifier in the input network traces, we apply recursive analysis and validation. First, we try to replay each request in the input network trace one by one. Then, we obtain the leave response and compare it to the original response in the input network trace. There are two possible cases. If they are the same, go straight to the next request. If they are different, this means that the response may contain a session-specific identifier. In this case, we get their different byte regions and try to use a predefined constraint solving list to identify them. After the detection, this module derives a list of message rewrite rules. It records the detailed information of each identifier. For example, this rule shows the message rewrite rule for the session ID identifier, including its source, reference, and their relationships. And this is for the tree ID field. Based on the derived rules, DynPRE established an on-the-fly message rewriting mechanism. It's used to dynamically recognize and extract the identifiers from server responses, and then adaptively update the corresponding value in request during the interaction. Now, let's move on to the second part. We use an active approach based on request message probing. In detail, for the input network trace, DynPRE analyzes each request-response pair in turn. To analyze a request-response pair, DynPRE first replays the preceding request to put the server in an appropriate state. Then DynPRE flips each byte individually to form probe requests, sends them to the server, and collects the corresponding responses. On the one hand, these additional responses can be used as semantic indicators for the corresponding bytes. The semantic equivalence of 2 bytes corresponds to the semantic equivalence of the corresponding responses. If 2 consecutive bytes are judged to be semantically equivalent, they are considered to belong to the same field. On the other hand, since the responses are usually received passively and are difficult to probe, we use traditional statistical analysis. These additional generated responses can enrich the samples for statistical analysis. Finally, we use a refinement process to further improve the accuracy of inferred formats by synchronizing the request and response results. In this process, we also form the type of each message. For the evaluation, we compare DynPRE against 5 reverse engineered tools and evaluate their performance on 12 public protocols. We provide those tools with the same input network traces. In terms of the format inference, DynPRE have a 50% perfect fair inference rate, which is 1.6 times to 3.3 times higher than other toys. As for the state machine, message type inference is the key to state machine construction, and we treat message type inference as a clustering problem. As a result, we use the widely accepted clustering metrics, particularly mentioned as metric for state machine inference. The results show that DynPRE achieve 11% to 22% higher remission than other toys. To further illustrate the effect of dynamic inference, we provide the compared toys with enhanced datasets. They are enhanced by dynamic interaction. In detail, we provide two types of enhanced datasets. The first is the set of additional message samples derived by DynPRE, donated as DynPRE. And the second is the message samples derived by protofuzzer bufers, donated as bufers. The results show that the improvement for the compared tools is limited, and some results are even worse. DynPRE is still the best. This is because they use different strategies to explore the interactive traffic. DynPRE explores by associating modification operations with server feedback, while other tools rely solely on statistical analysis. Finally, we also use DynPRE to analyze the priority protocols used in several IoT devices. To achieve this, we design a 3-step evaluation process by considering protocols application. In the first step, we active various behavior on the target IoT devices via the official app. Meanwhile, we capture the network traffic during the activation and use the traffic as the input for DynPRE. We then use DynPRE to infer the message format related to each device behavior. Finally, to evaluate the results, we use the inferred formats to generate new messages. We then send these new messages to the device and observe what behaviors they can trigger. The results show that based on the formats inferred from the original traffic with 7 behavior types, the newly generated message can trigger 15 different behaviors on the selected devices. In summary, DynPRE utilizes the server's interactive capability for protocol reverse engineering. It supports adaptive message rewriting and applies an exploratory request probing methods for analysis. So that's all I have. Thanks for listening, and I'll take questions.
Nice work. So let's see if we got any questions.
Hi, thank you very much for your talk. I was wondering if your techniques might generalize to encrypted protocols like TLS, where some of the fields are observable, but other fields contain maybe ciphertext or random values?
Unfortunately, we can't because TLS uses the encryption.
Okay, so these techniques don't generally apply to encrypted protocols?
Yeah.
Okay, thank you.
We got any other questions?
That's very interesting talk. My question is about statefulness of the server. So what if the response is different, not because of the session identifier, but because of the current state of the server? For example, I'm asking like, what is the time from the server? It can give a different value every time, right?
Sorry, I didn't understand the question.
Okay.
What's the
So,
question?
say I'm requesting time from the server. Now I'm sending a response. It will give you some time like 12 o'clock, something like that. After 1 hour, if I'm going to go to the server, it will give me a different value, right?
Do you mean the randomness in the responses?
State-based randomness, yeah.
Oh yeah, we actually we have some mechanism to deal with this, and due to the time limitation, we didn't present in our presentation. We will send the probe request to the server multiple times, and compare their response to deal with the randomness in the response.
Thank you.
Thank you.
Any other questions? We can take one more question. I'll ask one. So I understand you cannot handle encryptions. What about checksums? Like CRC checksums, can you handle that?
Yeah, actually we can use some existing tools to deal with the checksum. We can, such as CRC check. This is actually discussed in our paper. We can integrate existing toys to deal with the checksum.
Thanks. So let's thank our speaker again.
Thank you.